I think it's high floating meeting control system.
Okay. So. Yes, okay, so. Yeah, multiplication is a binary operation, so you can multiply two things at once. So if you have multiplication of 3 elements, you either multiply the A and the B first, or you multiply the B and the C first. If we go up to 4 variables, well, you can do it all just from left to right, multiply A times B, then multiply that times C, then multiply that times B. Or you could do it, I guess, right to left, do the CD first, and multiply B times that, and then multiply A times that. Or in pairs, multiply A and B, multiply C and D, and then multiply them together. Or, yeah, so you could do the B and the C, and then A times that, and then times D, or the B and the C, and then that times D, and then A times that. So there are 5 ways. Anyone want to guess how many ways there are when n is 5? A, B, C, D, E. 14. It is 14. And they're there. So yeah, if there were 2 elements, you just have one multiplication. There's one way to do it. Okay. Now let's talk about another example: triangulations of a convex polygon. So a triangulation of a polygon is a decomposition into triangles by inserting non-crossing diagonals. So you start with a triangle, it's already triangulated. If you have a square, or it could be any quadrilateral, just use square, you can insert one diagonal and you decompose it into triangles. If you insert both diagonals, you also decompose it into triangles, but the diagonals have to be non-crossing. And then when you have a pentagon, there's 5 ways to do it. So you basically pick any vertex, and you have to have the 2 diagonals coming from that vertex. And then when we go up to a hexagon, it goes up to 14. Basically, you could have any of the 6 vertices and those coming out of that vertex. You could have any of these ones that are like an N shape. I think there's 6 of those, and then there's 2 of these that are like a triangle. So once again, you get these same sequence of numbers: 1, 2, 5, 14. A lot of problems in combinatorics involve putting balls into boxes with various conditions. And in here, we're going to count the number of ways to put n indistinguishable balls into n boxes, such that the first I boxes together have at most I balls. So like, for instance, if n is 3, then we're looking for ways to place 3 balls in the boxes, such that the first box has at most 1 ball, the first 2 boxes together have at most 2 balls, and the first 3 boxes together have at most 3 balls. But there are only 3 boxes and 3 balls. So that last thing I said out loud is unnecessary here. And there are 5 ways to do that. So you could have all 3 balls in the third box. But if you have a ball in the first box, that has to be at most 1. And then if you have a ball in the first box, you can't have 2 balls in the second box, because the first 2 boxes together have to have at most 2. Okay. And for n equals 1, there's only 1 way. The box, only 1 ball to put. Right, 1 ball, only 1 box to put it in. For n equals 2, there are 2 ways. You can't have 2 in the first box. You could have 1 and 1, or 2 in the second box. And it goes up to 14 when you have 4 boxes. And so you get this same sequence here. Okay, and so what is this sequence we've been seeing? So 1, 2, 5, 14. When you see that in combinatorics, just about always it's going to be the sequence of Catalan numbers. It starts 1, 2, 5, 14, 42, 132, and so on. Yeah, well, there's 2 1s here, but the 0th Catalan number is 1 as well. There's a recursive formula for these. The Cn+1 is the sum of the this convolution here. So, like for example, this 42 here is if you do 1 times 14 plus 1 times 5 plus 2 times 2 plus 5 times 1 plus 14 times 1. So this is C0, C4. Then this gives you the 5th Catalan number, which is 42. You do the sum here. So, and then once you know that, you can use this recursive formula to find C6. And there are some explicit formulas. The most commonly seen one is 1 over n+1 times 2n choose n. So this n choose k is n factorial over k factorial n minus k factorial, which is just a number of ways to select k things out of n things, k unordered selection. So like 52, like how if you have a standard deck of 52 cards and you're selecting 5 cards, there's 52 choose 5 ways to do that. So then if I take this formula and divide by n+1, I get this, which can also be split up into 2n choose n minus 2n choose n plus 1. So there are reasons for having different formulas, like how to show that some of those things we saw earlier, triangulations, balls in the boxes, parenthesizations, are counted by Catalan numbers. Well, one way to do it is you can show it satisfies this recursive formula with the given first term. So yeah, that initial condition and the recursive formula fully define the Catalan numbers. So one way to show that a set of objects are counted by this number is to show that they satisfy that initial condition and recurrence relation. So before we get into that, also some of the history of Catalan numbers. So apparently this Mongolian astronomer and mathematician in the 18th century came across these numbers in this identity for sine of 2 alpha in terms of powers of sine. Euler encountered these. He conjectured in 1751 the number of triangulations of a convex n-gon to be Cn minus 2. So one of the examples we saw. And Goldbach and Segner helped Euler complete the proof, and then the first self-contained complete proof was later. But they're named for Eugene Catalan, who wrote it in this form and showed it to be the number of ways to parenthesize multiplication. So over a century later, that Reardon introduced the term Catalan numbers. And this book came out in 2015. Richard Stanley published a book. There's 214. We've only seen 3 of them so far in this talk. There's 214 combinatorial interpretations of the Catalan numbers in this book, along with 68 additional related problems. So Richard Stanley is the most prominent name in combinatorials among those that are alive today. And in the online Encyclopedia of Integer Sequences, OEIS, the Catalan numbers have the longest entry in there. And I think even some of them wrote in there that the sequence had the longest entry, and rightfully so, or something like that. So one of the problems that's in this text is consider the following chess position. Black is to make 34 consecutive moves, after which white checkmates black in 1 move. black may not move into check and may not check white, possibly on his last move. Black and white are cooperating to achieve the aim of checkmate. Apparently, this is the type of problem that people that study chess actually look at, even though in actual chess that I've seen, you don't make 34 consecutive moves. But the solutions are in here in the somewhere. So this A6. So there's an explanation, but yeah, it ends up being the number of solutions is the 17th Catalan number. I don't know if I mean 17 is half of 34. I don't know if you change this to another even number, if it's going to be half of that, half of that, or I don't know. The position of the pieces seems really random. Like, what if you change those? But I don't. Yeah. Anyhow. So now let's actually prove that the ways to parenthesize multiplication of n elements is the Catalan number C n-1. So you can show the base case n equals 1, and then assume that it's true. So we're going to use basic induction. Assume that there are ck-1 ways to parenthesize multiplication of k elements. And then what we're going to do is we're going to start with the last multiplication to be performed. So it's going to be the first so many times the first so many. And these are smaller than n. So there's ck-1 ways to parenthesize this, and c gets to be n-k-1 ways to parenthesize that. And then just as an example, so like if you have n equals 6, there's 1 way to parenthesize a, and 14 ways to parenthesize this, as we saw earlier, the b, c, d, e, f. If the last multiplication to be performed is this one, well, there's only 1 way to do this. But then there are 5 ways to do this multiplication. Here it's 2 and 2. This is the last multiplication to be performed. Or here, there's 5 ways to do A, B, C, D. If A, B, C, D times E, F is the last one to be performed. And then 14 and 1, you see we get exactly this, what's written up here. And yeah, in general, you get that recurrence relation. So in general, we have that. Okay, let's do something similar for triangulation. So just like how we had the parenthesizations and we wanted to split it up somewhere, based on like the last multiplication to be performed. Here we want to pick a way of splitting it into 2 smaller polygons and triangulating those. And so what we're going to do is we're going to remove an edge from the polygon to split it into polygon with fewer sides, and I'm just going to pick the top one. Doesn't matter which one you pick. I'm just going to pick the top one. And so it boils down to, how did you triangulate this, and how did you triangulate this? Well, it gets a little bit tricky because sometimes, sometimes depending on which diagonals you're including, you might get a different one. And there's one kind of special case here. This thing doesn't look like a polygon, but it's essentially considered like a 2-gon. So there's one way to triangulate that to no triangles. So that's that C0 equals 1 case. Yeah, it's also a theorem. This balls in the boxes problem counted by the Catalan numbers. I'm not going to go through the proof of that, at least not now. So I don't know why this keeps showing up. Hopefully the screen is still sharing. Did somebody write anything in the... Okay. I'm going to talk about what my graduate advisor Tom Roby calls the nervous politician problem. He was a student. He got his PhD under Richard Stanley at MIT. Basically, there's two n votes cast in a political race, and the two politicians, A and B, and they each receive the same number of votes. So no matter how you count them, no matter what order you count the votes in, it's going to end up tied. But apparently, A is very nervous, and the bad things are going to happen if he's trailing at any point. So how many ways can we count the votes so that A is never trailing B? So these are called ballot sequences. So there are 5 ways when n is 3. You can count all the A's and then the B's, but you got to start with an A, because A can never trail. And you can't have an ABB, because then B would be ahead at some point. So yeah, this way A is ahead and then B, this one B tied, and then A pulled ahead and B tied at the end. So, okay. And these are also counted by Catalan numbers. And one way to explain this by splitting it up into smaller cases is you have 2 times n plus 1 votes. You can basically start with an A at the beginning, and at some point we know that it's going to be tied again. Maybe not until the very end. You started AB, the first time that would occur is right away, but find the place where the first tie occurs, and maybe you can't count all this, but this is where the first tie occurs. And then take out that A and B and divide it into smaller ballot sequences. Each of these has to be a ballot sequence, because if B pulled ahead of A here, then when you put the initial A there, that B would be the first place where the tie occurs. Maybe, and again, you could have an empty ballot sequence. If it started AB, then the first one would be empty. If the first place the tie occurs at the end, then the last one would be empty. That's where that C0 comes into play. Okay, so yeah, satisfies that recurrence. And okay, another one for those that attended my I had a seminar talk earlier. I talked about these. Deep paths of length 2n are lattice paths that have up steps, so diagonally up or diagonally down, that never fall below the x-axis. So here n is 7, because this is 2 times 7 length. And instead of splitting this into smaller deep paths, which you could do, we're going to just come up with a bijection between the ballot sequences we just did and these deep paths. So every up step corresponds to an A, every down step corresponds to a B. So we have a 1-to-1 correspondence between those ballot sequences and these deep paths. So yeah, the condition that A is never trailing is equivalent to the condition that you never pass below this x-axis. Never at any point when you're reading left or right have more down steps than up steps. Any questions so far? Okay. Another one, you recognize this 5 as the third Catalan number. So if you have 2 endpoints in a row, actually you have an even number to do this, you can pair them up with non-crossing arcs above the points. So you want to pair them up, like this is paired with this one with this, and this with this. But we're not allowing a crossing, we're not allowing anything like this. And these are also counted by Catalan numbers. Okay. Well, we can come up with a bijection between these, and ballot sequences. I'm using L's and R's instead of A's and B's, but yeah, basically write an L for each left endpoint and an R for each right endpoint. And then I know that this L has to go with this R. This L can't go with this R, then what would this L go with? They have to cross. So yeah. Okay. Yeah, to go the other way, you could scan from right to left and match every L with the leftmost available R to the right of it. So, I guess I could do. So this R. So every L, okay, so scan from right to left. So every L with the leftmost available R to the right of it. So kind of like, I mean, it's kind of like when you're reading parentheses, if you have like a open parenthesis, you find like the rightmost, you find the like it's got to be this, and then yeah, you can't have this because then it would cross. So it's going to be like that. Okay, but non-crossing matchings are counted by Catalan numbers. So are non-nesting matchings. So here it's the same idea. You're pairing up the vertices. And you're allowing crossings now, but what you're not allowed to do is nest them like this. You're not allowing that. So this is also counted by Catalan numbers. This bijection works considerably easier. So the first L goes with the first R. The second L goes with the second R. The third L goes with the third R, and so on and so forth. It's easier to explain at least. Yeah. So there's non-crossing matchings and non-nesting matchings that are counted by Catalan numbers. There's also non-crossing partitions. So in those last two examples, we had two n points. So here n was 3, but you had 6 points. You needed to pair them up. Here, you're partitioning them into subsets, but they don't need to be pairs. You could have some singletons, you could have some threesums, and so on. So here we have n points. Here I'm doing the n equals 4 example. So does anybody remember what the fourth Catalan number is? 14. Well, here are the 15 partitions of this set. So one of these is crossing, the other 14 are non-crossing. So which of these partitions is crossing? This one. We have this crossing that. Good. The others are non-crossing. Okay. This image is from Wikipedia. If you look at the page for partition of a set, there are 52 partitions of a 5-element set, but the fifth Catalan number is 42. So 10 of these must be crossing. We find which 10 those are. Row 6. 1, 2, 3, 4, 5. You mean 6, like
Yeah, not counting.
yeah. This one, yeah. So these are crossing, and
/1.
so this one is the So these are crossing as well. Yeah, these are organized, so like you rotate these, you get these 5. So this one, for the one at the top, you rotate it, you get it stays fixed. Okay. Another one that I didn't know about until I found, was famous, and then found this in Stanley's book. This one about stacking coins. So the nth Catalan number also counts the ways to stack coins in the plane, with the bottom row consisting of n consecutive coins. So there are 5 ways to stack coins. If you have 3 coins lined up against each other at the bottom. So you could not have something like this, because then gravity would pull it down. But if you have coins on both sides, then that if I have this, I can't have this unless I also have this here. And so this is what I'd like to give you. You can talk to people.
This one is just another model of the heat path where every half point is staff. And then the top point is where it goes to the points.
Yes, so there's a bijection between these and deep paths. Yes, very good. So if I just place I guess this one I have to go up and then down. Yeah. And then if we're including this, I'd go up here. Yes. So what I'd like you to do now is to have some paper if anyone wants it, and you can work in groups or individually, and if anyone wants pencils or pen, here they are. And so 5 is the 3rd Catalan number. 14 is the 4th Catalan number. So try to see if you can write out all 14 ways to stack coins with 4 on the bottom. 4 consecutive coins on the bottom. See if you can figure out all 14 ways to stack coins. 14 with 4 on the bottom. 14 ways.
So I assume this also shows that the number quarter ideals of a root coset of type A.
Yes,
minus
Catalan
1.
numbers, yeah.
Catalan.
Yeah, there's a lot of, I only have time to, talk about it.
Practice is very.
Not- I meant to say, we had non-crossing matchings on two endpoints, we had non-nesting matchings on two endpoints, we had non-crossing. Partitions on n vertices, there's also non-nesting partitions on n vertices that are counted by Catalan numbers, but it's a bit trickier to explain what that means. Triangulations had non-crossing in it, non-crossing diagonals. I had the idea once to try to come up with the same definition, make sense of the non-nesting, but that didn't work.
There's always only one crossing value, both non-nesting and non-crossing. Unless you're just
Yeah.
like, that's right.
Yeah.
I think that they're. So we could have, of course, nothing on top. We have nothing on top here. We could have one on top that could be in any of three places now. What else could we have? Two on top, spread all over the place,
Okay, so they could be anywhere. They could be this and this.
which is just
Same thing, but now it's one this thing instead of one B.
Yes, this and this. Or this and this.
No, two big pyramids.
Okay,
Those are sometimes the first. Two more.
like. This, yeah,
Then you scoot it up around,
good.
and now you're done. Now you got it going. Now you just put a picture up there. That's all the cases.
So yeah, if you have all three here, then it's just. Those, or. One on top on the left, or one on top on the right. Or. Two on top, or. Going all the way to the top. Good. And yeah, someone. Pointed out, these are in bijection with deep paths, so up until then this, I guess, gotta go up like that. Yeah. Okay. Here's an interesting one. The distinct terms appearing in this product, where you multiply x1 times x1 plus x2 and all the way up to I think this should be an xn actually here, yeah, probably cn. So I'm actually going to give the name just a, b, and c. When you write this, you don't know how many letters there are, or you don't. I have to write it like that. But when you multiply a, you get one term. When you multiply a times a plus b, you get a squared plus ab, two terms. When you multiply times an a plus b plus c, you could take your previous answer, multiplied by a plus b plus c, and you get 6 terms, but 2 of them are alike and they combine. So you get 5 distinct terms. Hey, let's see what happens when we.
So you turn all positive coefficients into one, essentially, right?
Yeah, so combine the like terms and we get 5 distinct terms. If we didn't combine the like terms, it'd be n factorial. Then we're gonna, yeah. So now we can do this for put an a plus b plus c plus d here. And so we can take our answer to this. And then multiply this times a plus b plus c plus d. And so we get a cubed a to the 4 plus a cubed b plus a cubed c and a cubed b. And then 2a squared b times a is 2a cubed b. And then 2a squared b times b, so 2a squared bc and 2a squared bd. And then a squared ca, so that's a cubed c, a times a squared bc, and then a squared c squared, a squared cd, a squared b squared, a b cubed, a b squared c, a b squared b, and a squared bc, a b squared c, a b c squared, and a b c d. So where do we see like terms that we can combine?
squared BC.
We have a 2a squared BC and an a squared BC, yes.
Go down the left, get another a squared BC.
Oh, wow, yes. We want to cut out, yeah, we want to cut out 10 terms. So that's 2 that we can cut out of 20.
A cube C. A cube C,
A cubed C, I see one of them here,
first row.
one of them in the first row. So let me just combine this, the 2a cubed C, and then I can subtract this one. This one becomes a 4a squared BC.
AB squared C as well, the lower left.
AB squared C.
In the current lower left. Then upper row,
Yes, so that becomes 2ab squared C.
a squared B squared,
A squared B squared.
and red above it.
Ah, yes, this will become a 3.
A
Down, looks like a 15, so there should be one more, unless I wrote something wrong.
two A cube B's. First row.
Yeah, this one, there's 2 of them here to combine with this one. So we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 distinct terms. So as I said, there's 214 and counting through there's more known combinatorial interpretations of Catalan numbers. So, we can come up with bijection between those. 214 choose 2 pairs, although several of these have, technically there's multiple bijections, and sometimes there's multiple natural ones to use for different reasons. So there's actually more than this total bijection between them. But these 2, until you found bijection between all of them, you keep looking. So let's look for more bijections here. So 2 of the things we've seen earlier, parenthesizations of multiplication of n+1 elements, and valid sequences with 2 n votes. And so these are actually paired up according to a bijection that we're going to talk about. So can anybody see how that bijection works? Maybe it helps to include the unnecessary parentheses around the last multiplication. So all multiplications now have parentheses around them.
So that's where you found the number, where you have a.
Maybe it helps to color code things. So I color coded these in red and green, and these dots are in green here.
It's not like the possible.
See what's going on? So if you read the left parentheses and the multiplication dots from left to right, it's just, replace the left parentheses with A and the multiplication dots with B. Okay. Let's revisit this example. Well, here we got like an A cubed D, which came from A times A times A times B. And we got a squared BC, which came from a times b times c, or a times b times a times c, or a times b times c times a. That's why we got 4 of them together. But you don't see a d squared anywhere, because the only place you can get a d is from this last thing. You see a c squared somewhere, a squared c squared, a times c times c. You don't see any c cubes, because there's only 2 c's that you can multiply together. So these are products with 4 variables, with at most 1 d, and most 2 c and d combined. Not only do you not see a c cubed, you don't see a c squared d. If you have a c squared, it has to be this times this, in which case I did not select the d from this last one. And most 3 b, c, and d combined. That sounds similar to something we saw earlier. The boxes, yeah. So this is just like distributing balls in the boxes labeled B1, 2, 3, 4, such that B1 has at most 1 ball, that corresponds to the D's. B1 and B2 have at most 2 balls combined, that corresponds to the C's and D's together. Yeah, so like A, B, C squared, no D's, 2 C's, 1 B, 1 A. 1 0 0 3, 1 D, no C's, no B's, 3 A's. So yeah, they correspond exactly with balls in the boxes according to the conditions we saw earlier. So they're counted by Catalan numbers. Okay, so we talked about if we know one thing is counted by the sequence of Catalan numbers, then if you have a bijection between that set and another set, they're all counted by the same sequence. We saw that for instance, parenthesization of multiplication satisfied this recursive formula. And therefore, we just came up with a bijection between those and valid sequences. Valid sequences are also counted, the same sequence. But where do we get this explicit formula from, where I can just plug n into? Well, there are a couple ways. There are a couple different approaches to do this. You could, there are more explicit ways to do this. But one, the one that I first saw is to use generating functions. So a generating function is a power series, like what you saw in Calc 2, power series, but where what we really care about are the coefficients. So the coefficients of x to the 4th is the 4th Catalan number. So we can just, typically when we talk about generating functions in combinatorials, we don't care about what the interval of convergence is. We don't care about like plugging in a value. We it's just one way to write the entire sequence in one line, essentially. But it's extending forever this way. And then if we can come up with a formula for this, we can figure out what this is. There's a property of generating functions that basically, like if you were to multiply, well, anyhow, I'm not gonna. If you multiply 2 power series, like the x squared term could come from like an x from this term times an x from this, or from an x squared times a constant term, and so on. So this looks like we have 2 different sequences here, but here we actually have the same sequence. This looks like that recurrence relation. So that's Cn plus 1 when you multiply f of x times itself. So multiply f of x times itself. A and B are both the Catalan numbers, so you end up getting this, and then basically you can use the f of x squared equals f of x minus 1 over x. And then you can solve that with the quadratic formula where f of x is your variable and x is like a coefficient. So we get x in our answer. You have to figure out why this is the minus and not the plus. but you end up getting this, and then this series is known that the coefficients are 1 over n plus 1 times 2n choose n. So you didn't get to don't have time to talk about that, but I had my students in combinatorics reflect on which thing they learned felt the most creative and why, and several of them said generating functions, just really neat tool to come up with a lot of to answer a lot of problems in combinatorics. So that's one way to show this explicit formula from the recursive formula. All right, so I'm a combinatorialist, but maybe you have interested in other areas as well. I thought I'd include a couple things that like here's an infinite series. This we do care about what it converges to. The reciprocal Catalan numbers. So 1 plus 1 plus 1/2 plus 1/5 plus 1/14, and so on. Any guesses as to what this converges to? E. It is not E. It is 2 plus 4 root 3 pi over 27. It's a special case. You plug x equals 1 into this. This series is this on its interval of convergence, which is -4 to 4. But there is a similar one with a simple answer, and that is the sum of 4 minus 3n over the nth Catalan number. That is 2. I think you can manipulate this to turn it into that, because how would you get the n? Well, you can take the derivative of this and get an n out front. And then you get an x to the n minus 1, but you can just multiply the whole thing by x. So you can manipulate this and actually come up with that. Yeah, so thank you. And are there any questions?
Questions? I was interested, can you go back a couple slides? Yeah, that's right. So when you say from the binomial series, I mean, I guess you're using that on the square root of 1 minus.
Yeah, so
And then you divide out, but again, you're ignoring radius because certainly the C and XN must have radius convergence 0, right?
no, this has a. I think the radius convergence is. Well, there's a division by x, so it looks like, well, x can't be 0, but actually, like, if you have.
Well, so, yeah,
Yeah,
like,
yeah,
what
like
I'm saying is like,
something
it would have to be
this,
some kind of
that
totally
was
algebraic
like-
thing, right?
X going to like.
Right, because the series itself, the C and XN, isn't that like 1 over n plus 1 and then like 2n choose n? I mean, that's gotta have radius convergence 0, right? The actual, the power series, if you gave it to a Calc 2 class and asked them to compute the radius convergence.
No, the radius convergence is not 0.
Okay. But of course, right, I mean, there's some kind of algebraic business going on.
Yeah, there is.
Like if you were to plug in some number of x.
Right, so.
Well, okay, so yeah, if x is 0, you're taking the limit as x goes to 0. Like how you can come up with a series for sine of x over x, and it doesn't have the division by 0 problem. It's the same thing here.
Right, because.
The
I mean,
numerator has a constant term of 0, so dividing by x, so we ignore the division by 0 problem. And that's actually how you know it's a minus instead of a plus from the quadratic formula. If it were a plus, the numerator would have a non-zero constant term.
Yeah, that's right. Other questions?
So before you were talking about the A times A plus B times A plus B
let's see, you can also do a bijection with this second column, right, where the fourth row has at most one ball. The second row has at most two balls. Third row has, most.
Well, this, it would be the first and second row together have at most two balls. I'm not sure how you, because like. Well, first of all, if you know the second row has two balls, whatever that means, if what positions are they in?
Oh, I'm talking about top. So,
Oh, the top, okay, so,
that one has at most, it either has 0 or 1. And then
Yes.
the next one down, is 1, 0, 1, or 2. Like one
next
down.
one, yeah, but if the top one has. 0, if it has 1, the second one can't have 2, but this has a 1 and a 2, so.
So there's one out of the. Yeah, one. Yeah,
Maybe you could do it. Wonder if you could do it diagonal, because if you know. You know how many balls there are
This
diagonally, like, you know, there's 3 balls in this diagonal, you know, they gotta be here, but. I mean, there's some. There is some bijection between those, I don't know that it's easy to say.
Okay.
But yeah, nice ideas.
That's the first thing that I thought when you said like, which might go.
Yeah.
Yes, the 2 months I top count too. I think the right risk versus 6.4. That's cool. Honestly, work that out. So, other questions? All right, let's thank our speaker. Thank you. Oh, this is your check. Anybody out there have any questions?
We get the things. We had this presentation.
Yeah.
Stop share.
Any questions? All right, well, remember the math in tomorrow. Thank you all for coming by, and we will catch you on the flip side.
Should we get to start recording?
Yeah.